Welcome to this online lecture that includes the topics matter and temperature. All right, so before we start talking about matter, I want you to take a second to look around the room and kind of make a mental note of what you see. In the room I'm in, I see a TV, I see pictures, I see a radio, I see clothes, I see a window, and outside the window I see trees and a blue sky, my kid's little swimming pool. So everything that you're seeing right now is made of matter. Okay? Everything that you see is made of matter. Some things you actually can't see, but it's still made of matter. For example, as I look through my window, okay, I can't see the air, okay, that, is around me constantly that I breathe in and breathe out, but it is matter. All right, so there are some things that I can't see as well that are still matter. If I look at my arm, okay, I can see probably the smallest thing I can see on my arm is, the little tiny hairs and the little crisscross divots of the skin. But inside, making my skin up, are cells, individual cells, which I cannot see. And inside those cells are proteins and DNA and all that stuff, which I can't see, but it's still matter. Okay, so matter is anything that's huge, anything that's really, really tiny. Okay, as long as it has volume and takes up space, whether it's the DNA that takes up space inside your cell, okay, or the entire Earth that takes up space inside of our solar system, it is still matter. And we can see that, just looking around your room, that different kinds of matter have different properties, right? So how is the water in my water bottle sitting right here different from the air that I am breathing, okay? The same air that's rustling the trees outside. Okay, how's it different? How's it the same? How is salt different from sugar? And how is it similar? Okay, they're both white little grainy substances. If you saw both of them in a little dish, would you know which is which? Right off the bat. Okay, so they look very much the same, but they have very, very different tastes, right? Sugar is definitely sweet, and salt, not so sweet. Okay, salt is salty. All right, so as chemists, we always want to know why. Okay, that is the huge answer, or the huge question is chemistry is why. Okay, why is different kinds of matter different? Why do they have different properties? Why is salt and sugar both white, but salt tastes salty and sugar is very sweet? Okay, what's the difference there? So in this chemistry course, we are always going to ask ourselves, why? Why? Okay? And we're going to investigate and answer our whys as we take a look at matter. So like I just alluded to in the last slide, matter is anything that occupies space and has mass. Okay, whether it's super, super, super tiny mass, times 10 to the negative 9th mass, or times 10 to the 10 mass, okay, huge mass. As long as it has mass and takes up space, it is matter. Now, matter, as you should know, is ultimately composed of atoms, and those are the fundamental building blocks of matter. So the thing that all matter has in common is that it is made of atoms. Okay, it's very general. But every kind of matter out there has that one thing in common, is they're all made of atoms. They may be made of different kinds of atoms, but they're definitely all made of atoms. And usually these atoms are bonded together to form what we call molecules, which are two or more atoms joined together in specific geometric arrangements. So for example, if we have this little can of Coke here, okay, can is made out of aluminum, all right, and so we can see here's the aluminum atoms, like a representation, I should say, of aluminum atoms. If we take a scanning microscope and we actually scan the surface of something and take a look at the atoms, this is what atoms actually really kind of look like. They're little spherical balls. They look kind of like clouds in the sky, depending on what background, obviously, that they're photographed against. But they're just kind of fuzzy dots is the best that we can take a look and picture atoms. But aluminum atoms here, okay, a representation of these aluminum atoms is very much different than if we had rubbing alcohol, which is another kind of matter. But rubbing alcohol's atoms kind of look like this. We can see that the geometric arrangements are quite different. In the can, it's very structured, crystalline in shape. But in the rubbing alcohol, they're kind of all clumped together. In fact, we can see molecules versus atoms. See, these individual dots here, or circles, spheres, represent the atoms within the aluminum can. Okay, because aluminum is not a molecule or a compound, it is a pure metal. So it just has atoms that are kind of joined together, or sitting together, not really joined together, but sitting right next to each other. In rubbing alcohol, on the other hand, we have molecules. We have different atoms. We have carbon, hydrogen, and oxygen atoms. They're actually bonded together to form molecules. And those molecules are free to move around each other. So if we take a really close look, we can see that, hey, maybe this right here is a molecule. Okay, and this here is a molecule. But you can see they're all kind of clumped and floating around each other. So those are molecules. It's very different arrangement than the atoms within the aluminum can. And we kind of alluded to it in the last slide, but matter can be classified many different ways. Okay, one way could be the state of matter. There's three common states of matter: solid, liquid, and gas. And you probably have learned this from elementary school, right? In the solid state of matter, the atoms or molecules are packed very closely to each other and they're fixed in that location, meaning that they don't really move. They may vibrate right next to each other, okay, but they don't move around. Solids may be crystalline, okay, in which they're arranged in repeating geometric patterns, just like we saw the cube kind of structure within the aluminum can in the last slide. Or they might be amorphous, okay, not really having a geometric pattern. So there's actually a picture right here that's on this slide. This is a crystalline solid where you can see it is, nice geometric repeating pattern. All right, we've got big, little, big, little, big, little, big, right? And by, joined on all four sides to a little one is a big one, and joined on all four sides of a big one is a little one. It's super, like, repeated geometric pattern. On this side, though, is what we call amorphous solid, okay, where it's not really, doesn't really have any order. It's kind of all random, okay? So that's what that's the difference between the two. Now, in the liquid state of matter, atoms and molecules are next to each other, but they're free to move around and by each other, okay? So they have a little more freedom. They don't just vibrate next to each other. They can wiggle and move around and slide around each other. So it gives it a little more freedom in the liquid. In fact, if you notice something that's solid versus something that's liquid, something that's solid has a definite shape and volume. Something that's liquid has a definite volume but not a definite shape. You can pour it into other solid objects and it will take the shape of whatever object that it's in. The last state of matter that we're going to discuss is gas, the gas state of matter. And in the gas state, atoms and molecules are separated by large distances, so they're not really anywhere close to each other. Gases are what we call compressible. Because the atoms and molecules are not in contact with each other, they can be compressed or be forced to be more in contact with each other. If you think about compressing a or for example, if you think about an aluminum can like we had, right? If you open up the aluminum can and you pour out all of the liquid and it's just full of air, okay, you can put it on the ground and pretty easily crush it with your foot, okay, because the gas inside is very compressible. If you take that same aluminum can and you don't open it, you leave the liquid in there and you try to crush it with your foot, okay, it's super hard, maybe even impossible with, you know, your own foot, maybe a giant's foot or something. And you know, to go one more, if you freeze the can and now it's all solid, it's even more difficult to crush. Okay, so as molecules become separated by larger and larger distances, they become more easily compressed. We can see here in this picture that, you know, that here's a container with gas molecules that are spread out. We can put a weight on top to compress them so that they are closer together in this picture, and we can put two weights on top of them so that they're even closer in this picture. Okay, maybe even so close that they form or condense down into what we call a liquid state of matter. All right, so this little graphic here, what should be a little more clear on your handout, is basically kind of a summary of, you know, solid, liquid, gas states of matter. How the physical properties of shape and volume, fluidity, compressibility, all that stuff. So you can take a look at that, and most of it, if you can kind of visualize things in your head, most of it could be, you know, common sense, like shape has fixed, solids have fixed shape, gases take up whatever shape is in their container. Solids are not very fluid, it doesn't flow easily. If you think about, you know, pouring, if you have a pitcher of iced tea with ice in it, right, the tea part flows nice and easily, the ice kind of clunks out, doesn't really pour very easily. So a lot of this stuff is pretty common sense if you can tie it to something concrete, something part of your world. So as you study chemistry and as you, you know, take a look at these different rules and properties of matter and stuff like that, the easiest thing to do, the best way to learn it is to compare it to something that you know, something in your world that you know, like iced tea, okay, for example. Just kind of get it a little more solid in your brain. All right, so let's move on to classifying matter in a different way. So we can classify matter like we saw as solid, liquid, or gases. We can also classify matter as elements, compounds, or mixtures. Okay, so we can classify matter as pure substances or mixtures of substances. So a pure substance is going to be composed of only one type of atom or molecule. Okay, so two types of pure substances. We either have elements, okay, pure elements, so something like the aluminum can that is only made up of aluminum is going to be a pure substance made of the element aluminum. Okay, it can't be broken down into any similar substances. All right, a compound is two or more elements in fixed proportions. So that was, like we saw earlier, the rubbing alcohol. Rubbing alcohol could be considered a pure substance because it is, you know, or a compound, I should say, because it has the carbon, hydrogen, and oxygen molecules together, okay, bonded together to make the isopropyl alcohol that is in the container. Now, on the other hand, if it's not a pure substance, it's what we call a mixture. And a mixture is composed of two or more different types of atoms or molecules combined in variable proportions. Okay, that is kind of key. So a mixture is not really constant. You could have one part of the mixture have, for example, a mixture could be salt water, like the ocean, right? In one part of the ocean, you know, nearest the shore, the salinity may be higher. There might be more salt molecules or crystals in that part than, way out in the deep part of the ocean. Okay, so mixtures have variable proportions. The majority of matter is made up of mixtures of some sorts. So we've got, in fact, I do have to kind of let you know that rubbing alcohol is probably not pure rubbing alcohol. It's probably mixed with water. So it is a mixture of water, water, H2O, and isopropyl alcohol. So there's two types of mixtures. One we call heterogeneous, and the other is homogeneous. Heterogeneous is composition varies from one region to another. One way we can think about heterogeneous is that you can see the parts of the mixture. Okay, so if we think about a taco, with the shell and the meat and the cheese and the lettuce and the tomato and the sour cream and the little hot sauce on top. Okay, that is a mixture because it's made up of different types of molecules combined in variable proportions. And you can actually see the parts. You can see that the shell is different from the meat molecules, which is different from the lettuce molecules, and so on and so forth. So if you can see the parts of the mixture, then we call that heterogeneous mixture. A homogeneous mixture is the composition looks the same throughout. So you can't see the difference. Okay, so you can't see the parts in a homogeneous mixture. So for example, that bottle of rubbing alcohol that I said was probably not pure rubbing alcohol, but mixed with water. You can't see the water versus the rubbing alcohol. Okay, but there is two types of molecules in there: water molecules versus rubbing alcohol, isopropyl alcohol molecules. So that's what we call a homogeneous mixture because it looks the same throughout. If you think about Kool-Aid, okay, growing up with Kool-Aid, at least I grew up with Kool-Aid. Kool-Aid is a mixture of water and basically just sugar, okay, and some food coloring. So those three ingredients, those three types of molecules inside, but you couldn't see the difference between the water and the sugar versus the food coloring. It's not like they separate, okay? So that's a homogeneous mixture. Oil and water, though, is a heterogeneous mixture because if you let it settle, okay, it'll separate into an oil part and a water part, okay? So that's the difference between the two. Here's a nice schematic of classifying matter as elements, compounds, and mixtures. So all matter, right, is can be classified, like we said, into pure substances or mixtures. Pure substances can either be elements themselves, like the aluminum can, or compounds, okay, like water. Mixtures could either be homogeneous mixtures, like inside that aluminum can is usually, if you buy a Coke can, it's going to be Coca-Cola, which is a mixture. A homogeneous mixture is where, again, you can't see the difference between the parts. They all kind of look the same. So sugar water is a homogeneous mixture. Heterogeneous mixture is where you can see the parts. So, I guess definitely if you think about soda can, the compressed carbon dioxide within it that makes it all fizzy and bubbly is, if you add that to the mixture, then it kind of definitely becomes heterogeneous because you can see the bubbles of the carbon dioxide within it. Okay, so if you can see the parts, it's heterogeneous. If you can't see the different parts of the mixture, it's homogeneous. So most of the material, like I said, that we encounter in this world are mixtures. The air we breathe is a mixture of oxygen, nitrogen, and other gases. Oceans are mixtures of water, salts, and other substances. Kind of everything is a mixture. Your cereal, in the morning is a mixture. The milk that you pour your cereal in is a mixture. So most things are mixtures. And the important thing to realize here is that the properties of matter, no matter what kind of matter it is, the properties of matter are determined by the atoms and molecules that compose it. Okay? So properties are always determined by the atoms or molecules that compose it. So when you're cooking and you burn your hand on the, on the metal pot that you're, boiling water in, even though the water's not hot yet, okay, you still can burn your hand on the pot. Why? Well, metal has a different property than water. Okay, so because of the different atoms and molecules that make up the metal versus the water. So properties of matter are determined by the atoms and molecules that compose it. All right, so here is an old scientist, Antoine Lavoisier. He was a French scientist back in the 1700s, I believe. He studied matter, okay, and he established what's called the law of conservation of mass, which basically says there's not ever new matter. Okay, matter is neither created nor destroyed in a chemical reaction. So if we take matter, for example, if we take salt and we dissolve it in water, okay, the little salt crystals are not destroyed, all right, and we didn't make anything new. We just dissolved the salt within the water. Or if we actually take a look at a chemical reaction and we react carbon and oxygen gas together to make carbon dioxide, okay, however much carbon and oxygen we started with is the exact amount of carbon dioxide that we have to end with. So that's what we call the law of conservation of mass. Whenever we are working with a chemical reaction, for example, that carbon and oxygen one, like I had mentioned before, which is right here, if we start out with 12 grams of carbon and 32 grams of oxygen, you will make 44 grams of carbon dioxide. Okay? Because none of the atoms or in the molecule are destroyed and no new ones are created. Okay? That is what we call the law of conservation of mass. So here is where you can prove to yourself that the law of conservation of mass is definitely a law of science. Here's a you try it problem. A chemist forms 16.6 grams of potassium iodide by combining 3.9 grams of potassium with 12.7 grams of iodine. Show that these results are consistent with the law of conservation of mass. So why don't you pause the video? I know you won't, but pause the video and do the math and see if you can get it to show that the law of conservation of mass is definitely in place here. And then unpause it and I'll show you if you're right or wrong. All right, so here we go. We're given 16.6 grams of potassium iodide is formed from 3.9 grams of potassium and 12.7 grams of iodine. So what do we need to find? Well, we need to prove that this law is true, that we say what we start with equals what we end with. And so if we take a look, 3.9 plus 12.7 is definitely equal to 16.6. So we can see that law is definitely takes place in this equation or in this problem. So law of conservation of mass says matter is neither created nor destroyed. However much you start with is going, mass-wise, is going to equal the mass of what you end with. And if it doesn't, then some escaped somehow, okay? Or if it's heavier than what you ended with, then it must have reacted with the oxygen in the air or some kind of atoms in the air around it that pulled those extra atoms down to increase the mass. Either way, atoms are neither created nor destroyed. All right, let's take a look at the last part of the lecture, which is about temperature. So atoms and molecules that compose matter are in constant random motion, okay, which means that they may contain thermal energy. Yes, even solid matter is in constant random motion, vibrating motion, okay? Not necessarily free-flowing motion that we can see, but vibrating motion that perhaps we can't see. And even like the cells within our skin, which on the large scale is, pretty solid. However, the cells that make it up, there's free flowing of, ions and proteins and all that stuff within the cytoplasm that we can't even see at this larger scale. So there's definitely constant random motion going on. And that constant random motion means that basically contains thermal energy. So temperature is the measure of a substance's thermal energy. How those molecules and atoms are moving, how fast or how slow. The faster they move, the higher the temperature. The slower they move, the lower the temperature. Okay, heat, on the other hand, this is kind of maybe kind of confusing to think about it at first, but heat is different than temperature. Heat is a unit of energy, and it is the transfer or exchange of thermal energy caused by a temperature difference. Okay? So if we take a look at this example, this picture right here, okay, this middle picture, we have the same amount of heat, okay, being produced, okay, or same amount of heat transfer going from the Bunsen burner to the beakers, the water in the beakers. But the temperature of the water is going to be different for both beakers. All right, there's a smaller amount of water in beaker A, so we can say that heat that's being transferred is going to be moving those molecules in the water a lot quicker, okay, so that the temperature is going to heat up a lot faster in beaker A than in beaker B. Beaker B is going to take a lot longer to heat up because that same energy that's being transferred is going to, it takes longer to get all those molecules moving, okay, at a higher speed. Okay, so even though they have the same amount of heat that's going to the that's being transferred from the flame to the water, the temperature is going to be different. So see, heat and temperature are definitely different from each other. Okay, this picture over here is kind of representing the same thing. If we put the same amount of heat, okay, towards these two different substances, one that has a large heat capacity, one that has a small heat capacity, the larger heat capacity is going to take a longer time to raise the temperature. The one with the smaller heat capacity over here, that temperature is going to rise very quickly. Okay, even though the same amount of heat is being transferred to both. All right. You can think about it, in terms of real world, boiling water for spaghetti. Okay, just like I was talking about a few minutes ago. The pan, okay, even though the heat coming from your burner, okay, is this constant same amount of heat that comes up. It's not really any, on the mass scale, not very different. Okay, that heat exchange is the same, but the temperature of the metal versus the water is going to be different. The temperature of the metal is going to heat up a lot, is going to rise more quickly than the temperature of the water. Okay, again, why? Because different matter have different properties because of those atoms and molecules that it's made from. All right, so let's take a look at the different ways that we can measure the temperature, the thermal energy inside of matter. There are 3 different temperature scales that we can measure thermal energy with: the Fahrenheit scale, Celsius scale, and the Kelvin scale. And you are familiar with all 3. Fahrenheit is what we use in the United States to measure the temperature of most things. We do the weather in degrees Fahrenheit. Right now it's 96 degrees Fahrenheit outside. Nice and cool, 78 degrees Fahrenheit inside of my room here. Celsius is basically used by scientists, okay, and people in other countries as well. That's kind of the metric unit, I guess we could say, for temperature. And then scientists also use what's called the Kelvin scale when we're mostly when we're talking about gases. Okay, when we're investigating different gases and how they behave, they're going to use the Kelvin scale. And the Kelvin scale is nice because it avoids zeros. So there's no negative numbers on the Kelvin scale. Now, when we take a look at Fahrenheit, and please always remember that my little program that I use hates to do apparently superscripts. So these little degrees things should be, up on top. So Fahrenheit is degrees, degrees F. Basically, where that came from was the guy named Fahrenheit used water freezing, okay, and set that at 32 degrees Fahrenheit, and the temperature of water boiling is at 212 degrees Fahrenheit. Why? I have no idea. I guess just to confuse us. Celsius, on the other hand, is nice and easy. Water freezes at 0. Water boils at 100. Okay, so it's a nice scale from water freezing to water boiling. And Kelvin, like I said, avoids negative temperatures because 0 Kelvin is the coldest temperature possible. So when all molecular motion virtually stops, that is what 0 Kelvin is. And scientists have reached within 0 Kelvin, but never 0 Kelvin as of yet. So if we take a look at the right-hand side here, in this graphic we can see the different temperature scales and how they compare to each other. So at 0 Kelvin, the coldest temperature possible, that would be equal to negative 273 Celsius and negative 460 degrees Fahrenheit. Okay, here where water freezes, okay, we can say that in Celsius it's 0 degrees, Fahrenheit 32 degrees, and in Kelvin it's 273 Kelvin. Water boils up here, again, remember at 212 Fahrenheit, 100 Celsius, 373 Kelvin. We can see that Kelvin and Celsius, okay, are have a nice fixed scale that go together. There's a 100-degree difference between freezing and boiling for both of those scales. For Fahrenheit, on the other hand, it's not 100 degrees. Okay, so Fahrenheit is much more difficult to work with. So in chemistry, we're going to be working with either Celsius or Kelvin. So when we're working with either Celsius or Kelvin, we're going to have some equations under our belt in order to figure out how they're related. So here are some equations that will be helpful for you guys to know. When we are working with or need to convert to Kelvin, what we do is we take the Celsius and we just add 273. Okay, or if we're given Kelvin and we need Celsius, just rearrange it and subtract 273. All right, here's why I said Fahrenheit was such a pain in the butt. Here's the conversion equation for Fahrenheit. Okay, so if we need to solve for degrees Celsius, you take your Fahrenheit, you minus 32, and then divide that by 1.8 to get degrees Celsius. Okay, so it's a little bit of a pain in the butt. In fact, here's a pain in the butt example for you to do now. Convert 310 Kelvin to Fahrenheit. So to figure this out, we're going to write down, we're going to think about this. We're going to write down our given, right? We're given 310 Kelvin, and we need to find, according to our question, we need to find degrees Fahrenheit, right? How many degrees Fahrenheit is that? Well, we need to know, right? What do we need to know? Well, we need to know or use these equations right here. So that's going to kind of be our tool belt for solving this problem. So to solve it, we're going to, first we need to go, what's our solution map? All right, so we're going to go from Kelvin. All right, we don't have a particular one to go from Kelvin straight to Fahrenheit, so we need to go to degrees Celsius. Then we can go to degrees Fahrenheit. Okay, so why don't you stop, do that, and then replay it and see if you got the right answer. All right, so you should have gotten 98.6 degrees Fahrenheit. So that's the kind of the average normal body temperature. So next time you take your body temperature, if it's 98.6, you can think to yourself, hey, I'm 310 Kelvin, thank you. All right, so this was the math, the correct math that you need to do that work. So first you need to use the equation to convert Kelvin to Celsius. You should have gotten 37 degrees Celsius. And then plugging that Celsius into the second equation to solve for degrees Fahrenheit, you get 98.6. However, if you are a really good chemistry student, you would be like, hey, sig figs, what about those sig figs? And you'd be totally right. Okay, so if we take a look at the number that we start with, how many sig figs do we start with in our given? 2. All right, and remember equations and things within the equations, like this 1.8 and such, don't count for sig figs. So we technically need to round this to 2 sig figs, okay, or no decimal points, because we don't have any decimal points to begin with, so we shouldn't have any decimal points to end with. So technically with sig figs, your final answer should be 99 degrees Fahrenheit. Dun, dun, dun. Oh, sig figs, I love you. All right, so there you go. That wraps up our lecture on matter and temperature.